Okay, so on the screen here I've got two graphs that you'll come across a lot of the time in stats. This graph on the left, this is a probability density function, a PDF, and this graph on the right is the cumulative distribution function even. So let's just explain what these are one at a time. So if we start on the left, the probability density function. So all this graph tells you when you take a reading is the probability that you will get some value x. So say I had on this graph here x was, I don't know, 10. Well, I could read up, and this is the probability that I would return that x value, and obviously this is going to be some number that is less than 1. So we know then that if any reading of this graph is going to be the probability of getting some value of x, then all the readings off the graph must add up to the total probability. So that is the sum of x. Sorry, this should be the sum of p, even the sum of probabilities for all x between 0 and infinity should equal 1. Now, for a discrete range of data, you can just add them all up, but probability density functions are continuous ranges of data because you can read off at any point. So if we want to find the continuous area under the graph, what we do is we integrate. So to find the the integral of f of x, that is the function that generates this graph. So we're going to say that this line is generated by f of x between the bounds of now infinity and negative infinity. In specific cases, you only need to integrate between the bounds of the data. So say here we said that there's only some probability between 0 and 100, say, then we'd integrate between 0 and 100, but this is just general form. And this is always, for this graph, going to equal 1. That's because it's the area under the graph. Now, for a cumulative distribution function, what are we being shown by this? Well, the cumulative distribution function, if we said for the probability density function that the reading off the graph tells you the probability of getting that specific x value. So say we took the same reading when we took x equals 10, and we read off. And we said this was the cumulative distribution graph for the same function that's generated this density function. So what would we be told by this? Well, this value of x, this value for x is 10, is found by doing the sum between 0 and 10 of all probabilities of x. So that is the this is the cumulative probability function at x equals 10. And of course you can just replace 10 with n and give it for any n. So when we read off the graph, instead of just telling us the probability of getting a specific value, this means it's telling us the probability of getting that value or any lesser value. So what we've done then, to go from a PDF to a CDF, is we've said, instead of just taking a specific reading at 10, we've taken readings from all points below 10 and added them up. That is, we found the area between negative infinity and 10. So to get the function for a CDF, we take f of x, the function for our PDF, and we integrate it between bounds of, well, we'd normally say negative infinity and some value x. And because we've got a variable in our bounds, this is going to output some function which we'll call capital F of x. So that's how you produce a cumulative distribution graph from a PDF, just by integrating between bounds of negative infinity or x, or whatever the lower bound of your data is. So for example, in this case we could say, oh well, the lower bound of our data is 0, so we could integrate between 0 and x, and that'll give us the cumulative distribution function. So that's the basics of PDFs and CDFs. To go this way, you integrate, and then obviously to go back, you just differentiate the function. A PDF tells you the probability of getting any specific value, and a CDF just tells you the probability of getting any specific value or less.